Hello and welcome to Solved, where we help you solve problems. In this video, we will be discussing the material balance process for a distillation column. Distillation is one of the many separation processes that you will encounter, which aims to split the feed into its components by virtue of the differences in their volatility. Here's the problem statement. A liquid mixture containing 45% benzene and 55% toluene by mass is fed to a distillation column. The overhead or distillate product contains 95 mole percent benzene, and the bottom product leaves with 8% of the benzene fed into the column. The volumetric flow rate of the feed stream is 2000 liters per hour, and the specific gravity of the feed mixture is 0.872. Determine the mass flow rates of the distillates and bottoms and the composition of the bottom stream. Let's go ahead and solve this problem. We have here our representation of the problem. Here is our distillation column, and as you can see, it has three process streams. One of the three process streams is the feed, which is the only input stream, and you have two output streams. Those are the distillate and the bottoms. The distillate contains more of the lighter or the more volatile component, while the bottoms contain more of the heavier or the less volatile component. That is how distillation works, okay? We are separating two components on the virtue of their volatility. Our two components are benzene and toluene, and our feed stream contains 45% benzene and 55% toluene. These are given in percent by mass. The composition of our distillate is given in mole percent, that is 95 mole percent benzene, while the remaining 5% by mole is understood to be toluene. So we would have to convert this to a mass percent before we proceed to the material balances. We are also given another information that 8% of the benzene fed goes to the bottoms. That is 8% of the benzene in the feed. Our given flow rate of the feed is in a volumetric flow rate, that is 2000 liters per hour. And we were given a specific gravity of the feed. So we would have to convert this volumetric flow rate to a mass flow rate before we proceed with the balances. And for this problem, we are required to solve for the mass flow rates of the distillate and the bottoms, as well as the composition of the bottom stream. As with any material balance problems, whenever you're given compositions and flow rates do not agree with each other, you have to make them all in mass units. For example, the volumetric flow rate will be converted to a mass flow rate, and the compositions by mole in the distillate will be converted to a composition in terms of mass. Let us first set our basis to 1 hour operation. This comes from our volumetric flow rate, which is given in liters per hour. So setting a basis for 1 hour makes sense in this case. Now let's convert the flow rate of the feed. So if you have 2000 liters of F, we just have to use the density to convert this volume into mass. However, our only given is the specific gravity, that's 0.872. We can convert that to a density by multiplying that specific gravity with the density of water. For simplicity, let us represent the density of water as 1000 kilograms per cubic meter, or 1 kilogram per liter. That means that our density is 0.872 kilograms per liter. Canceling our units, that is 2000 multiplied 2.872. The mass of stream F is 1744 kilograms. This value is what we are going to use for the material balances. You cannot use volumetric flow rates for the balances. Okay? Now let's take a look at the distillate. We are given a composition in terms of percent by mole, and we have to convert that to percent by mass. We are going to set a temporary basis, that is 100 moles of D. Take note that this temporary basis has nothing to do with our original basis, that is 1 hour operation. This temporary basis of 100 moles of D is only applicable in this part of the solution where we are trying to convert from mole percent to mass percent. Okay? So if our temporary basis is 100 moles of D, that means that we have 95 moles of benzene and 5 moles of toluene. We can use their molecular weights to convert these moles to grams. The molecular weight of benzene is 78.11. That is grams per mole. While for toluene, that is 92.14. Multiplying, that is 95 moles times molecular weight of benzene, 78.11. The mass of benzene is 7420.45 grams. While for toluene, that is 5 times 92.14. We have 460.7. From this hypothetical mass values of benzene and toluene, we can solve for the mass fractions of benzene and toluene. Let us represent mass fractions with the variable W so that we will not get confused. The mass fraction of benzene in this case is simply the mass of benzene, 7420.45, divided by the total, 7420.45, plus the mass of toluene, 460.7. That is 0.9415. Of course, the mass fraction of toluene is simply 1 minus the mass fraction of benzene because it's a binary mixture, and that is 0.0585. These mass fractions are what we are going to use for the material balance. Now, let's proceed to our bottom stream. It was mentioned that 8% of the benzene fed goes to the bottom stream. So we are going to take 8% of 45% of 1744 kilograms. That would be 1744 is the total mass of your feed stream. 45% of this is benzene. So we can say that 784.8 kilograms is the mass of benzene in the feed. And we are going to get 8% of this, 0.08. This is the amount of benzene that goes into the bottom stream. Okay? So we know that in the bottom stream, there is 62.784 kilograms of benzene. We now have everything we need to perform the material balances. Let me first clear the board and then we'll proceed with the material balances. Our overall material balance, or OMB, is F is equal to D plus B. We know the mass of our feed, that is 1,744 kilograms. That's equal to D plus B. This is our equation 1. The 1744 comes from the conversion from volumetric flow rate to mass flow rate using the specific gravity value. Next, let's have a component balance. We have two components, that's benzene and toluene. But if you take a look at the given, toluene is only represented in the feed and in the distillates, and we don't know anything about the toluene present in the bottoms. So it would make sense that our component balance is for benzene because it is complete. Let's perform the benzene balance. That is 0.45 times F is equal to 0.9415 times D plus 62.784. 62.784 is the amount of benzene that we have determined coming from the 8% of the benzene coming from the feed. Since we already know the mass of the feed, that is 1744, we can immediately solve for D. By rearranging, this becomes 0.45 times F1744 minus 62.784, and this is divided by 0.9415. The mass of D is calculated as 766.88 kilograms. Accounting for our basis, which is 1 hour operation, this also becomes kilograms per hour. Now that we know the mass of the distillate stream, we can go back to our equation 1 and calculate the mass of the bottom stream. That would be F minus D. We calculate the bottom stream as 1744 minus the distillate stream, that is 977.12 kilograms per hour. With that, we were able to solve for the flow rate of the distillate and the bottoms. And what's left is we need to know the composition of the bottom stream. To solve that, let me represent the mass fraction of toluene in the bottom stream as X. By doing so, toluene is now represented in all of the streams and we can perform a toluene balance. The toluene balance is 0.55 times the feed, 1744, is equal to 0.0585 of the distillate column, 766.88, plus the toluene in our bottoms. That is X times bottoms, 977.12. Remember that X is the mass flow rate of toluene in the bottom stream. Coming from this toluene balance, we can directly solve for the value of X. That is 0.55 times 1744 minus 0.0585 times 766.88 divided by 977.12. X is 0.9357. This is the mass fraction of toluene in the bottom stream. Let me write that here. That's 0.9357. And to get the mass fraction of benzene in the bottom stream, we simply subtract this from 1. That is 0.0643. And that answers all of the requirements of the problem. The key takeaway in this problem is that a distillation column is represented with one feed going in and two streams coming out. That's the distillate and the bottoms. And that you should always convert everything to homogeneous units before proceeding. That is, we converted the mole percents to mass fractions and we converted a volumetric flow rate to a mass flow rate. Don't forget to do that and you won't have any problem with your material balances. That's it for this video. Thank you for being here and I'll see you on the next one.